welcome everyone to the lecture. Announcements, co-working and Q&A session after this lecture with Ankit for exercise 2. And the exercise 2 is due in a week. I need to do the recording for lecture 6 again. I haven't found the time. I'm sorry about that. I'll do it until this week, as I promised last week. Okay. Let's continue the training data attribution. I'll do a quick recap of what happened last time, especially towards the end of the lecture last time, because it was a little bit technical, and I had some more slides for explaining what's actually going on there, but maybe even before going there, maybe I'll just recap the formulation last time a little bit again. So the aim was to kind of treat the mapping from the training data to the model prediction on this particular test data of interest. Okay, so machine learning goes from the training data to the parameters, right? So that's the middle step, and based on these parameters, you're making the final prediction. So it's a chain of functions now. So we need to differentiate this first, and that is achieved by first assuring that this mapping is a function, first of all, and it's the differentiable function. And then we apply some kind of chain rule, because there are two functions, two mappings that are chained together. So first things first, so the mapping is not a function, as I said before. It's not a function. It's not, it's actually multi-valued. Given a training set, there may be multiple possibilities for the solution in general for deep learning, right? Depending on where you initialize the SGD steps, right, you may end up with different solution. So we made some assumptions to make this a function, first of all, and it's a function that is differentiable as well, which is making the whole kind of loss with respect to theta, the parameter, as a twice differentiable function and strictly convex function. Okay. Once we do that, then based on the implicit function theorem, we know that the solution is also a function of the individual data points that comprise the loss function. And then we can also compute the gradient, because it's differentiable. Okay, so these are the conditions. So the loss has to be twice differentiable against theta, and it should be strictly convex against theta. Okay. Some terminologies again. So we say Z for the input and the label together. We write Z for test sample, and Zi or Zj for training samples. We write L for the test loss for a single sample, and of course for the training objective we do the average over multiple loss values for different training samples, right? So that's the empirical risk that you have. Okay, and based on this empirical loss, you can define the overall solution, the global solution of this optimization problem, which is the argmin of the empirical risk. And this is again a unique solution, because L is strictly convex. Yeah, so if you sum over multiple strictly convex functions, you still have a strictly convex function. So the solution should be unique. The same is true for the summation over the training set, where Zj is excluded. You should also have a unique solution. So, and now your quantity of interest is the difference in loss values for the test sample Z, where the difference between these two cases are exactly whether you include Zj during training or not. Okay. Right. So to make this kind of sensible at all, we need some kind of a continuation of the mapping from the training set to the solution. And you know, the training set is actually a discrete quantity, right? It's a set. So for every sample, you have either decision whether you include that or in the training set or not. But actually, in terms of training, there's a way to kind of do it in a more gradual fashion, in a more continuous fashion, which is to say you can put some kind of individual sample-wise weight during training for the loss. So you have a summation over all the loss values over the training set as you normally do in empirical risk minimization. But on top of that, you have this epsilon times L of Zj, which is controlling how much weight you're going to give to this particular training sample during training. And again, this whole thing is strictly convex, so you have a unique solution, theta hat epsilon j. So we define this as theta hat epsilon j. And now we can treat theta hat of epsilon j as a function of epsilon. And it's a differentiable function against epsilon due to implicit function theorem. That's one thing. And the other thing that we realize is if you replace epsilon by -1/n, we recover this theta hat minus j before, because that's exactly, you're excluding this factor from this sum here, okay? So Zj is influenced from the sum, okay? So that's the trick. And if you define stuff in this way, then you have an intermediate lemma here, which is saying if you differentiate this theta hat against epsilon, and if you evaluate this gradient at epsilon equals to 0, then you're exactly going to get minus Hessian inverse times the parameter gradient of the loss at Zj, at the solution, theta hat. Okay. Where Hessian is defined as the average of the second derivatives of the loss against the parameter at different training points. So you're taking the second derivative multiple times at different training points, like millions of training points, and then doing the average of all these. And that's your Hessian. You take the inverse of that, and then do the matrix vector multiplication with the parameter vector, parameter gradient. So we did some proof last time. I'm going to skip that this time. Instead, I'm going to kind of give you some more intuition what this quantity is trying to do. Okay. Okay, so now I'm going to make things a lot simpler and express everything in terms of kind of three-dimensional surface. So now we have some sort of empirical risk or loss landscape that looks like this, strictly convex, right? Because everything is strictly convex. And now we have this original empirical risk given by the summation over all training samples. That's exactly when epsilon is 0. But let's say if your epsilon is exactly -1/n, you have instead this empirical risk, which is a summation over all loss values except for the term for Zj. And the optimal points for each case is respectively theta hat minus j for this one and theta hat for the original function. So the quantity of interest now is the change of rates for this theta hat as epsilon goes from -1/n to 0. Okay, and that is exactly this direction here, right? So let's say the planar kind of axis here is kind of the theta space, the weight space, okay? And you're basically wondering about the direction of the weight, which is pointing to the direction of the change in theta hat when you're kind of changing the value of epsilon around 0, okay? So this is the instantaneous change of rate for theta hat, okay, as you vary epsilon here. And the lemma is basically telling you that this vector here can be expressed as some kind of modulation or change, slight kind of modification of the parameter vector, where the parameter vector here is kind of pointing to the direction in the weight space where you're going to see the greatest change in individual loss value for Zj. Yeah, that's the definition of gradient, right? In the local vicinity, which direction should you take in order to increase the loss the greatest? Or if you take the minus step of that, that will be which direction is giving you the greatest decrease in loss value. Yeah. If a function is differentiable, these two maximal and minimal directions are exactly against each other. That's the definition of differentiability. Right. So now you have that direction, and you kind of slightly change the direction of this vector using inverse of Hessian. Actually, Hessian is a very special kind of matrix which does not change the direction of a vector super a lot. Yeah, because it's a symmetrical matrix, and its eigenvalues are positive thanks to the strict convexity of the loss value. I'm going to get to that later on as well. But somehow you can think of this theta hat gradient as some kind of originally some kind of directional vector pointing to the greatest change in loss value at Zj, but with a slight modification of the direction according to Hessian. Hessian is essentially encoding the curvature, local curvature of the loss value. The kind of image that I have when I think of Hessian is something like this. So like this paraboloid. When you compute Hessian, it's essentially kind of you're fitting some kind of paraboloid on your loss landscape locally. So of course your loss landscape is not a paraboloid, but if the function is twice differentiable, you can approximate the local changes in the around the point of interest with a paraboloid super well. Right. This is analogous to being able to approximate a surface, a differentiable surface with a tangent plane. So that's kind of a first order approximation of a loss surface. And now if you consider Hessian as well, you can approximate the original loss surface with a paraboloid, which is a generalization of a planar approximation, actually. Anyways, so once we have this kind of characterization of the theta hat change as epsilon changes, you know, like as a reminder, we have this training set, and then we have theta hat, and then we have the final prediction. But what we are wondering is how the final prediction looks like when you remove the training sample here. And so far, we have only talked about the first part, and now we talk about the second part and do the chain rule, okay? And the final quantity, again, is expressed in terms of L of Z, the test point, at theta hat at -1/n, and J minus the original loss, which is L of Z and theta hat. And again, I'm just going to write this down in terms of as a function of epsilon and evaluating the function at epsilon equals to -1/n here and epsilon equals to 0 here. And I'm going to turn this into some kind of notation for approximating a gradient, okay? Numerical approximation of a gradient. So if you do the division of this quantity here by 1/n, -1/n, this is exactly the numerical approximation of the gradient formulation, right? If 1/n is small enough, right, then this quantity is approximating the gradient against epsilon super well. So we can just write down that this is close to -1/n times the gradient of theta hat against epsilon evaluated at epsilon is at 0. Okay. So now this quantity looks quite similar to the dilemma we had before, except that the quantity here should be actually loss instead of theta hat. But now we can now apply chain rule. So again, this is the quantity that we are interested in, the loss change against epsilon. And then we can break this down into these two quantities. So first doing derivative of L against theta and evaluating this at epsilon equals to 0, which is exactly theta hat. And then doing the dot product between that and the rest of it, which is derivative of theta hat against epsilon, which is what we got from the lemma before. So now we have the minus of parameter gradient of loss at z times inverse of Hessian times parameter gradient at zj. Okay, so and you put some minus here, and we define that as the influence function, which is kind of approximating the instantaneous contribution of this single training sample for the final prediction for sample z. Okay, that's it. So that's influence function. Now I wish to give you a more detailed intuition of what this is actually computing. We know how this is derived, but we don't know, we don't have sufficient geometric intuition of what this is doing. So first, some basic kind of preliminary knowledge that we need to have is that if you have a symmetric matrix, it is diagonalizable. A symmetric matrix is diagonalizable. And even more so, the eigenvalues are real, and the rotation, the matrix that achieves this diagonalization is unitary or orthonormal. In other words, you can do kind of orthonormal change of basis in the vector space to achieve a diagonalization of the Hessian or a symmetric matrix in general. And each of the elements in the diagonals will be a real number. Do you know all this, or is this familiar to you? Okay, great. And now, Hessian is a symmetric matrix, and its eigenvalues are all positive because we had strict convexity in the first place. Yeah. So we are interested in the inverse of Hessian, right? We can write this down as Q transpose times lambda inverse times Q, where Q is a rotation matrix basically, and lambda inverse is diagonal matrix where the diagonals are inverted, and these will be all positive basically. And we can actually write down influence function as an inner product between two vectors. Okay, and the vectors will be, first of all, the parameter gradient for the loss at z, and another one will be parameter gradient for the training sample zj. And then for both of them, you're going to take some kind of rotation, the same kind of rotation, q, and then you're going to do some dot product, but that will be modulated by this weighting factor for each dimension given by the diagonals of this Hessian matrix. Yeah. Yes?
What does that mean, modulating?
So when you do, maybe next slide will explain this better. So, oh no, even the next one actually. So when you do dot product, you're basically summing over the products of each dimension, right? And for each dimension, when you do product, you do some weighted average. So it's a weighted average of each like element-wise product, right? And instead of just average, you take a weighted average of across the dimensions. So again, this is a generalized dot product between two parameter gradients, one for training sample and the other one for test sample. And Again, this is in a distorted space, so you don't think of this as a Euclidean space, but depending on the dimension, you think of different scales. Yeah, you have different scales for each dimension. So I'm going to give you an example. Yeah. So let's say we already chose a very good coordinate system for the vectors. So the Hessian is already diagonal under these spaces. And let's say we can write down the test sample gradient for this coordinate system as 1, 1, minus 1. And the training sample gradient will be 1, minus 1, and 1 for a three-dimensional weight space. And let's say the Hessian is a diagonal of 1, 2, and 2. If you take a normal dot product, then you're going to do 1 times 1 plus 1 times minus 1 plus minus 1 times 1, and that's going to give you minus 1. But in this case, we are taking an weighted average of these element-wise products. So you have 1 times 1 plus half times minus 1 times 1 plus half times 1 times minus 1. And that's actually going to give you a slightly different result than normal dot product, but not too much, right? As long as the weights are kind of uniform, right? Yeah, of course, in actual deep neural network, the Hessian matrix will have very skewed distribution of eigenvalues. So you'll actually have quite some chain, like quite some dynamics here in terms of weights you give for each dimension. But conceptually, you're still doing some kind of dot product here. Okay. So what's the intuition here? So again, Hessian is giving you some intuition about the curvature of the loss landscape at a local point. So you'll have some directions where loss is changing more gradually, and you'll have some directions where the loss is changing much more quickly. So you can think of this kind of plot. So along this direction, you have flatter changes, and the eigenvalues will be smaller. And so you can think of that as along this direction, the parameter is kind of less sensitive. However large you change your weight, the model will not react so much. Okay. And now for sharp directions, the eigenvalue will be higher, larger, and that means even if you change a small amount along this direction, your loss value will overshoot very quickly. To me, that's kind of telling me that when you train a neural network, not all the parameters are kind of living in the same scale. And by computing this Hessian, you can kind of get an intuition of which parameters are in which scale. And by doing the weighting according to the inverse of these eigenvalues, you can do the right scaling across all the parameters. So if a direction is, let's say, more sensitive, the loss values change more quickly along that direction, then we know that if your kind of gradients are either agreeing or disagreeing still with the same amount, right, between the training and testing, then that gives me a strong signal that, yeah, that's a very strong kind of dimensions, but somehow the loss values or the gradients, the loss gradients, parameter gradients, are still kind of operating in the same kind of scale. And that tells me that, okay, usually you should actually see a lot more changes in the loss values, but you're seeing the same amount. So I'm gonna kind of decrease the seriousness of these contributions when I compute the dot product. Okay, so right, so these are sensitive dimensions, and they are reacting the same way. So, okay, I know you're always sensitive, so I'll just not consider you as much. I'm not going to be serious about your complaints. Yes.
Okay, so as I understood, there are some parameters that contribute more to loss and some that contribute less. And there are also some that are more sensitive and some that are like have just a larger range where they're
So here, contribution is a little bit not super well defined. So I guess what I'm talking about here is only about sensitivity to small changes in the parameter values. So what I'm telling you is Haitian is telling us that if you go into that direction, how sensitive the loss will be, right? So that's one thing. And the other thing that we are considering is the parameter gradient, which is telling me if you make a small change, like delta amount of change in that direction, how much is the loss going to change? Well, actually, gradient is actually telling you the greatest change, the direction of greatest change in the loss value when you change the input by the same norm, same amount. So these quantities are, I would say, comparable, right? Because both are kind of telling you how much loss change you're going to have when you step into that direction. So when gradient is telling me that, yeah, if you step into that direction, then you're going to get 10 percent point more increase in your loss value, or 10%, yeah, 10% point more increase in the loss value. And then I realize, yeah, actually this direction is supposed to be very sensitive. Then, okay, it's kind of expected that you should get like 10% points more increase in that direction, and I'm not surprised. So I'm gonna kind of take this a little bit less seriously, and I'll put some factor to weigh this down. Yep.
So the motivation is that we want to have the influence function value reflect more the sensitivity that we get through the data change, less.
Yeah, exactly. Because eventually we are taking the gradient against the data, and Haitian is what comes out of this procedure. Yes.
So the inverse of the Hessian parameterizes such that
Right.
in all directions they're all the same.
Right. But locally, right? For every point in the space, the Haitian value will be different. So for every different points, you have to kind of have a different kind of metric in a sense. So okay. Yes.
Sorry, I have to ask again. So the gradient is getting me like the direction of x or xn.
Mm-hmm.
With the when you take the second derivative, the Hessian, what does the curvature tell you?
Another way I like to think about curvature or Haitian is you're fitting a paraboloid. So locally, your loss will look exactly like this. Okay, so Haitian is just telling me how much change in loss I'm going to have when I step into this direction versus this direction. So along the direction of steeper Haitian or larger eigenvalues, I'll see greater change in the loss value. So another way to think of Haitian is it's like a Taylor expansion or numerical approximation of the original loss value. Also keep in mind that at the solution, the gradient is 0 anyways. So the only contributing factor for approximating the loss landscape around the solution is Haitian itself instead of the gradient. Gradient is not giving you any change actually locally. So does that answer your question? Maybe not.
Yeah, I don't know. I'm just asking this. I don't know when I just have the gradient and the Hessian available. Like, is the Hessian trustworthy? How it what it wants to.
So maybe if you think of a more complex deep neural network landscape, maybe it doesn't tell you a lot actually. But at least for this kind of strictly convex functions, actually Haitian is a pretty good estimate of the overall landscape as well. So if you're listening to your Haitian and eigenvalues, I think it's going to give you a pretty good estimate. But of course, the caveat is that this is not always the case for, almost never the case for deep neural networks. So it's a different question in practice. Okay, so let's take a look at computational aspect of this, right? So we try to kind of approximate the expensive procedure of leave on out retraining, right? So which is kind of given the training set, I'm gonna remove one training sample at a time and then retrain the whole system multiple times. And that's super expensive, and that's why I came up with this kind of gradient-based approximation. But if you take a look at it, it's still very expensive because of the Hessian. Because the Hessian itself is a second derivative, which is itself quite expensive to compute. It's a p by p matrix, where p is the number of parameters. When it's a large language model, it can be p can be in the order of tens of billions or hundreds of billions. Not just that, but also Hessian is an average of all across all training samples. So yeah, you have to compute this n times where n is the number of training samples. Yeah, it's kind of eclipsed by all this huge computation, but also the gradients themselves are super huge. The loss gradient, the parameter gradient of the loss is in the order of millions or billions, right, depending on the size of the network, the number of parameters basically. And yeah, and then you now have to take the inverse of the Hessian. So for a p-dimensional, p by p-dimensional matrix, it takes p cubed time to compute this inverse in general. So when you do a naive computation, it's going to be big O of np squared plus p cubed, npq squared for just computing the Hessian, right? So that's dominating the influence function computation. So something needs to be done. In practice, this is almost never achievable, I mean, computable. So we are introducing LISSA algorithm to speed things up. I'm going to simplify the notation a bit. So I'm going to write V for this parameter gradient. And I'm going to write just H for Hessian instead of also writing theta hat. Yeah, it's always going to be theta hat anyways. So I write this Hessian inverse times vector product as H inverse times V. Okay, so now how do we compute this more efficiently? We have two ingredients. One is the approximation of the inverse of a matrix with a geometric sum. And then the second ingredient is by realizing that Hessian is a summation over a lot of individual Hessians over all training samples. And we have seen something like that before in SGD training, right? We are also kind of doing the training optimization over a huge number of samples, and you're basically taking some of like empirical risk minimization of that. And at each iteration, you're basically just considering a partial sum given by the mini batch. So we can probably do something like that here again. So we are seeking some kind of iterative solution here based on these two ingredients. Okay, so now for the approximation of the inverse with a geometric sum, the intuition comes from high school math, right? We know that when you have a geometric sum like this, where R is kind of the rate, you can express this in terms of 1 over 1 minus R, right? As long as R is kind of bounded between -1 and 1, if it's a complex number, it can also be kind of, yeah, within the disk. Yeah. And then now I'm going to turn this into this expression by just replacing R with 1 minus R everywhere. Okay, and then I'm going to have the infinite sum over 1 minus R to the power of I. And for this side, we're going to have 1 over 1 minus R, which is exactly R inverse. Okay, so we can write R inverse as this geometric sum. And the same actually holds for matrices. So if you define the I matrix minus H to the power of I and do some partial sum of these, up to t index, right? Then this quantity is approaching h inverse as t goes to infinity. Given that h is invertible, of course, and also given that the spectral norm of h is bounded by 1, meaning that all the eigenvalues are on the disk of this complex plane. And because, yeah, this is converging, right? And you know, the matrix vector multiplication is a continuous operation. So this implies that when you do multiplication with v as well, the quantity as well will converge to h inverse of v as well as t goes to infinity. And we are going to use that property for approximating h inverse of v. So essentially just turning an inverse operation into a sequence of matrix vector products. I'm going to write Wt for simplicity for this partial sum. Yeah, and the intuition is that when t is large enough, Wt is close enough to h inverse times v. And we're going to use this in recursion to kind of approximate Vt more and more closely to the target quantity h inverse v. And the exercise is to prove this equality here, given the definition of Wt. And given that W0 is v. Okay. So trusting that this quantity is correct, we go on with the second ingredient, which is stochastic approximation of the summation for the Hessian. So instead of just doing this recursion, we replace this h with one of the terms in the summation. We just randomly sample one training sample and then use the Hessian around this sample for an approximation of this Hessian. Of course, it's going to be super wrong, but you know, we also do SGD steps for training a neural network, and we're happy with the results. So why can't we just do the same for the Hessian here for each iteration? Okay. So this is all clear how you do approximation here? Okay. Yes?
Maybe not so clear why it's not a problem to not finish on one.
This may be a problem, but in practice, it works. So does that answer your question, or?
Well, I guess I believe you.
I also believe the papers. But yeah, it's good. I mean, we don't fully trust the results until we kind of see all the results in all kinds of situations. So I can also imagine that this will fail. But you know, like in this computation, we already made so many simplifying assumptions, like the loss is twice differentiable and it's strictly convex. These are already unrealistic, so it's okay to maybe do a little bit more approximation here. Yeah.
I didn't really understand why the eigenvalues of h are always complicated.
Yeah, so we are getting to that point actually. So, okay. So there are tricks to kind of ensure this is happening, right? So we can do some kind of dampening to and scaling to make sure that this is the case. So again, the condition for convergence here is that h is invertible and its eigenvalues are bounded below 1. But this is not the case in general. Well, for strictly convex and smooth, h is supposed to be invertible, right? Because all the eigenvalues will be positive. Yeah. But even so, the eigenvalues are not necessarily below 1. So how do you deal with that? So then what you can do is to kind of introduce some modifications of the Hessian to make this still positive definite and to scale the eigenvalues below 1. So you're adding this damping term for the diagonals of the Hessian by the amount d, ideally a very small amount. And then you're scaling everything down by s, okay? And when s is large enough, then the eigenvalues are supposed to be bounded below 1, yeah? So in this case, what you can do is can modify the original LISSA algorithm by v plus 1 minus di plus h over s, and then wt minus 1. Yeah. When d is small enough, and yeah, when d is small enough, wt defined this way will also approximate h inverse times v times s, actually. Yeah. And so we actually need to do 1 over s in front after computing this quantity to get back to h inverse times v, but which is not a problem because s is just a scalar, and multiplying this everywhere is not a problem in general. So yeah. So finally, the algorithm looks like this. So you first initialize v as the parameter gradient, and then you initialize w as the parameter gradient again. And for each iteration, we are choosing one sample, zjt, for each t, and then get the Hessian for that training sample. And then we do this complicated computation, but that's exactly the recursion formula that we saw before. And if you do that multiple times, then W is approximating S times H inverse times V. So we scale this down again with S, and then we get an approximation for H inverse V. So that's the LISSA algorithm. Yep.
And what exactly does damping?
Yeah, that's a good question. I almost missed that point. So the assumption here is that H is invertible, but in practice, especially with deep neural networks, this is not guaranteed because you may end up with a saddle point and so on. So in that case, you will have negative eigenvalues. But the hope is that even if they are negative, the size of the eigenvalues will be still quite small. And so you can only add a small bit of dampening parameter d along the diagonal to make the eigenvalues positive again, to make things all positive, definite, and invertible. So, and we don't do corrections for d eventually here because we believe d is small enough. Yeah. Okay. All right. So that's it for the. Yep. Sure.
So how do we get the DFS?
That's a good question. One way to get S, for example, is so sometimes you do just trial and error. You just try out different values of S, and then if things explode, then you scale things down, of course. Yeah, for D, I mean, S is not a big problem because you're anyways going to scale things down. So as long as S is in the range that does not induce any numerical error in your approximations, let's say S is super large, then scaling things down super small will kind of introduce some numerical errors. So you don't want to pick this to be a super huge quantity. But at the same time, you don't want to make this too small to make things not bounded by 1, right? So, but also like the allowed range of values for S will be, I would say, quite wide. So S is probably less sensitive to kind of the choice of hyperparameter. But for D, yeah, I think this could be a little bit tricky. I guess you can do some numerical exploration, for example. So you sample around the solution a few times and see whether how much the loss is decreasing on these points. And you can basically take the point with the greatest drop in loss. And then that's actually going to tell you a little bit about the minimal value of eigenvalue. And then you can basically add this value as the dampening parameter. But again, maybe there is a better solution. I don't have the answer top of my head now. I have a solution, but not the actual solution that people have. Yep. I think so, yeah. I think this is, I mean, LISSA algorithm is not very specific to influence function. It used to be there for a long time. Let's take a look at another method for attributing the training data. So we looked at influence function, and now let's take a look at tracking. I like to make an analogy. So influence function is like an input gradient in feature attribution, and now tracking is like integrated gradient for feature attribution. So what influence function is doing is you're taking a look at small changes in the model's reaction on a test data when you remove training data. So, and that's given by this formulation. Yeah. So let's do a brief recap of what integrated gradient is doing again. Yeah. Right, so we have test sample again, right? That consists of all features that are present in the test input. And you have a baseline without any features. And you draw a linear line between the two because it's a continuous space. This is possible, right? You draw a linear line, and then along the line, you kind of take a look at what kind of changes adding a feature I makes along this line. And you basically sum up all these directional changes along the path. And that becomes your integrated gradient for feature I. So that's essentially just taking these small differences in function values along this path x plus alpha x prime minus x, right? And then you're adding a small factor in feature I every time and see how that changes the function. And that's of course approximated by the gradient along this integral, and therefore you take the integral of the gradient along this path, and that's why it's called integrated gradient. And why do you do that? That also looks a little bit arbitrary, but you know there's the goal, which is completeness axiom. So if you attribute every feature I in this way, if you sum over all these features, all these attributions for all I, then that gives you exactly the total difference between the function value between f of x prime and f of x. Good. So can we build some kind of analogy to training data attribution? So I try to make everything quite similar here. We have, on the one hand, no training data, and we have, on the other hand, the entire training set. Okay. There's some path between the two, okay, whatever that is. And along the path, we're going to take a look at the impact of including / excluding a training data Zj. Okay. And this path is characterized by kind of adding training data gradually one by one. Okay. So now the question is how to set this path, right? And second question is for each point in this path, what is the contribution of Zj at each point? And once we have this contribution, we are going to kind of add all these infinitesimal contributions along the path. And that's going to be the total contribution of that Zj point along this trajectory. And then finally, the question is whether the so-called completeness axiom also holds for this kind of scenario as well. Okay, so first question, how do you set this path, right? It's a very conceptual path in this case. You know, the path is naturally given by the SGD training, because in stochastic gradient descent, you are gradually introducing a training sample one by one. Of course, after one epoch, you're kind of going back to the looping back and doing the repeating the same data multiple times, right? We can also think of this as a large language model training where you don't see the same data so many times, maybe once in general. So you're gradually adding in more and more data, and as you add more data, you're producing checkpoints. So think of a very kind of inefficient way of training a model where you're actually saving the checkpoint for every iteration. Every time you take a step, you take a checkpoint, okay? At each checkpoint, you can basically take a look at how the loss value is computed for this particular test sample of interest. Okay, and that's going to give you some sort of trajectory of how the loss value changes along the path of training. So I'm going to give you some illustration to make things more visible. So let's say eventually you're interested in this image here, which is a seat belt put on top of a zucchini. And since that's such a unusual image that you're going to see at test time, right? So now the model developers are wondering, yeah, why is this actually predicted as I don't know what should be the class, seat belt or zucchini? Seat belt, yeah. So this is predicted as seat belt, which is not a problem, but they still wonder why this is predicted as a seat belt instead of zucchini. So the first image that the model sees is a zucchini sample that looks like this, right? And when the model takes a look at this sample and makes the prediction for this case, actually the loss for zucchini is decreasing, meaning that this is more correctly predicted as zucchini as a result of seeing this sample here. So in other words, this sample is kind of a proponent to the prediction of zucchini for this test sample. Yeah. And then we have another example here, which is labeled as seatbelt. And this looks quite similar to the test sample here, but now with a different label. Now, so this is actually decreasing the likelihood of zucchini for the model for this image, and increasing the likelihood of seatbelt. So now this is an opponent, because now after looking at this sample, the loss value for this sample is increasing. And again, this water bottle, like tied to the seatbelt, is also labeled as seatbelt. So this is actually increasing the loss again. So now the influence here is negative again. And actually, you see the same sample twice, and now this time, for some reason, this is increasing loss value quite heavily. And so this is a strong opponent again. Yeah, you're basically accumulating the differences here for each training sample. And now we see another true zucchini image that's going to decrease the loss, and that's going to give high value for the influence for the correct prediction for this test image. And we have rather unrelated case here, which is still in the car, but it doesn't show any seatbelt. It doesn't show any, well, it shows seatbelt somewhere right here. But still the label is sunglasses. So this is not kind of hindering or helping the prediction of zucchini in the test image. So the influence is positive, but rather small. Okay, so that's kind of the idea here. So at every iteration, we kind of keep track of which samples, when added, these are kind of increasing the loss for this test sample or not. So in that sense, we are kind of tracking the contribution of every training sample across the training iterations. And that's exactly what you do when you kind of sum over all the influences along the path from no training sample to full training sample. This will actually be made more concrete in the coming slides. So I know I haven't dealt with Q2 yet, which is how do you attribute ZJ's contribution for each iteration. I'll get to that later. For now, let's take a look at the completeness axiom point of view. So, the eventual loss that we try to explain is after all the training iterations, you have the final solution, final checkpoint. And you wonder why the test sample Z has such a loss value after training, right? So that's a quantity of interest. And now you can break this down into multiple differences. So first of all, your starting point, at initialization, you kind of take a look at the loss value for this sample. And then for each iteration, you're making some deltas, right, at each iteration, which is given by L of Z and theta t minus L of Z at theta t minus 1. Some people call this telescoping series, right, because they kind of cancel out nicely. Yeah, so this is how you can write things down. And then we have some sort of, okay, and then we need to make a simplifying assumption, which is we are doing SGD training, and for each iteration, we are just taking a look at a mini batch of size 1. In other words, you're always taking a look at a single sample, generate a gradient for this single sample, and then take the gradient step, update the parameters, and then move on to the next sample. So for each batch, there's only one sample contributing. So between each checkpoints, there's only one sample involved. And that makes things a lot easier, how we can write things down. So for example, we can write down the tracking, so-called tracking ideal, as the summation over all these differences in loss values, where you're only summing over the iterations where the training sample of interest, Zj, is involved. Okay. Yeah, but in reality, right? Oh, before that, in this ideal case, we have completeness theorem satisfied, axiom satisfied. So if you sum over all the tracking ideal over all the training samples, yeah, then you're actually going to end up with the overall difference between the loss value for this test sample before and after training. Yeah. So basically, if you sum over all these partial sums over all training samples, then you're eventually going to get L at theta t minus L at theta 0. Yeah. It's basically a telescoping series. So in other words, this way you're decomposing the final loss versus no information loss into individual contributions of every training sample, okay, through this summation. So this looks very ideal and nice, but you know, we always have multiple samples in a mini batch, right? So for every mini batch, the question is how to attribute the contribution of each training sample in a batch to the loss update, because they are collectively kind of updating the loss value for every iteration. So how do we break this down? And then that brings us to Q2, question 2. What is the contribution of each data point Zj along the path? So as a starting point, let's take a look at the SGD update at time step t. Theta t is given by an update from theta t minus 1 plus some of the gradients, yeah, some of the individual gradients for every training sample in the batch. Of course, there are some factors in front given by eta t, which is the learning rate, this step size basically. And then you have batch size normalization. Of course, there are other factors like momentum, stuff like that, but we kind of disregard that for a moment. So let's take a look at this decomposition. Actually, this looks like a decomposition of the parameter update into individual contributions of each training point, right? But that's not the end of the story, because eventually what we need to do is to decompose the difference in loss between and after this iteration into individual training points. And this is only decomposing the parameter into different training points. And so here again, we can use the chain rule from the training data in a batch to the parameter update, and then to the loss value as a result of the parameter update. So we use the same trick again, chain rule and tail expansion. So now we can write down the loss value as theta t plus 1 as this one, where we plug in the equation for theta t plus 1. Okay, and we realize that eta t is usually small. the gradient step that you're taking is not like huge, and you're kind of moving away from the current iteration dramatically, right? You're always staying within the same kind of local vicinity. So we can use Taylor expansion here to kind of approximate this quantity. So this term here is small. So what I'm going to do is I'm going to assume that this is L of theta t plus some small amount, which is given by the gradient, some dot product between gradient and the small amount that you're going in that direction. And the small amount you're going the small amount you're going is basically this eta t plus sum over the gradients, yeah. And then the change of loss value along the direction is kind of given by the parameter gradient of the loss at theta t. And then there is some small term that will vanish more quickly than the linear term here. So I'm just going to use small o term for that. Okay, so this is the quantity. And now, given this, we can write down the difference between the loss values before and after this iteration as a summation over all the training samples in the batch, where you're taking the dot product between the parameter gradient for the training sample and the parameter gradient for the test sample. Okay. So given this kind of summation, the natural notion of contribution for sample Zj is exactly each of these terms in the summation, right? Because you're summing over all the training data here. So I'm going to say, yeah, this dot product between this loss gradient against theta for Zj and loss gradient for theta at Z as the notion of contribution for this iteration, for this particular iteration, yeah, T. So if Zj is included in the batch, right, then the contribution is given like this. If Zj is not in the batch at all, right, then of course the contribution will be treated as 0. And of course you have to sum over all the iterations, right? And that's going to give you track-in formulation. So contribution of Zj to Z is given by summation over inner products of the parameter gradients along the path. And you have some scaling factor eta t given by the learning rate at each iteration. So that's the definition of track-in. So far, no questions or? Okay. So I like to shed light on kind of the similarities between track-in and IF. Probably you noticed that already, right? In both cases, you're taking the parameter gradient of the loss at test time and the loss at a training point and doing some kind of dot product between the two. The only difference is that for track-in, you're not kind of modulating the vectors with Hessian. You're not rotating and doing the scaling of different dimensions. You're not doing that. You just take vanilla dot product here. Of course, you multiply this small scaling factor here depending on the learning rate at each iteration. So yeah, that's the difference here. And that actually brings me to some intuition around, or some kind of unifying framework for TDA, training data attribution in general, as a retrieval task. Because when you say you do some kind of a computation of that depends on the sample into some vector, and after computing the vector, you do some kind of inner product, and the first thing that comes to my mind is this is a retrieval problem. You do some embedding of the raw data sample into some vector space, and in the vector space you do dot product. Okay. So what is retrieval, right? The task itself is given a query, retrieve, kind of give me similar samples in the database. Yeah, that's what retrieval is. And the typical approach is you embed or you map every raw data point into a point in the embedding space, high dimensional embedding space. And then you kind of take the dot product between this queried point and every other point in the database also vectorized through the encoding. And then take the one with the highest dot product, yeah, the most similar sample. You can also do Euclidean distance if you like. Some people also do cosine similarity. It's based on your taste and what works actually well in each case. So the two ingredients are embedding function and some distance metric in this vector space, in this metric space. And training data attribution using influence function or tracking is exactly instances of this, right? So for influence function, the embedding function is given by the parameter gradient after the full training iterations. Yeah. So you do backpropagation for this given test sample Z. Yeah, you give this test sample and then you pass it forward through the network, and then you do backpropagation all the way through and get the parameter gradients, and that's going to be your embedding for this sample. And you do the same for the training data. Yeah? And then you take some kind of dot product, but the dot product is, of course, modified with Haitian. In tracking, actually, you're taking gradient several times along the checkpoints. And so you can basically concatenate all these parameter gradients at different checkpoints. And that's going to give you a pretty large high-dimensional vector. And then the kind of dot product you're taking is also kind of a modified dot product where the diagonals are given by the learning rates. Yeah. Yeah. So this is again some kind of retrieval task. So given this formulation, like unified view on stuff, we can also come with different ideas for how we can do this kind of retrieval task. Given a test sample, give me kind of similar training samples from the training set. Yeah. So from this point of view, people also came with different ideas for how to do training data retrieval using some more classical way of doing retrieval. For example, BM25 is more classical way of doing retrieval in documents, which is, I won't go into a lot of details. It's kind of handcrafted feature based on a lot of features, handcrafted features here. But yeah, it's not examinable. And that turns out to give you a pretty good result, for example. So compared to tracking, for example, this BM25 is giving you pretty good retrieval performance. Yeah, that's the main message here. So I know like tracking or influence functions are kind of giving you very good theoretical foundations for doing stuff, right? But in practice, maybe something else works so much better. So now the question is, what if you just do some usual ways of doing retrieval? So what if we just use feature embeddings instead of so-called influence embeddings, where you take the parameter gradient of the loss. So this parameter gradient of the loss is called influence embedding in some context. And you know, this is a huge dimensional vector. Depending on the size of the network, it can be like millions or billions. But you know, like in usual setting where people do retrieval of images or retrieval of text, they typically use a neural network encoder, like transformer encoder, and they just take maybe the final layer of the network as the embedding of the raw input, and that usually takes only thousands of dimensions. So it's like factors less computationally heavy than compared to the original influence embedding. So there's a lot of computational advantage for just doing something like this, like doing the encoding and then doing stuff there. But to me, this is still an unanswered question in training data attribution. As far as I know, there's no work on kind of illustrating the performance of this kind of simple approach in training data attribution. So I think it's worth exploring different options here and see what's working super well. I mean, BM25 here is kind of one example of that, but I think more studies should be done here. Okay, so that was one point. And now coming back to some foundations of training data attribution. Let's take a look at attributing not to a single point, single training data, but multiple of these. Okay. So why do we care about that? So we are kind of looping back to the 3 layers of abstraction in XAI. So we start from some real world problem, and then from there we identify a few useful tasks or quantifiable tasks, and then we do some approximation. In our case, we always um, revolved around leave on out retraining task, right? What happens if you leave this training data out of the training set? Yeah. And to me, that's quite well defined, yeah, but not so useful. So the motivation from 1 to 2 in that case is not very well established. The other problem, again, is that removing a single sample is usually very noisy, and the signal to noise ratio is very low. So with one PhD student from my group, LISSA, we did something called need finding study, which is a terminology in human-computer interaction, which is for new technology, we try to figure out what kind of needs people have, right? So there's some technology which is not there yet, but we do some kind of simulation of that technology and see whether people appreciate that. And we also get signals like, yeah, so this is the general direction, but on top of that, in which direction should we go to serve you better, right? So this is more kind of customer-centric kind of version of research, right? Where we don't just produce research and, yeah, look, if you like it, you take it. If you don't like it, cares, right? But we actually go to customers first and ask them if you need something, and we try to address these problems first. And that was very fruitful because we learned a lot from their feedback. So the people that we talked to are kind of model developers in different contexts, like in academia or in industry. And they all found training data attribution super useful for debugging the model, right? Because eventually, again, the kind of control you have over the model training is usually the training data. But they don't have a right tool for kind of analyzing the right the training data for achieving the result they want to achieve, right? And also, the kind of question we asked was, okay, now people are all looking at this leave on out retraining. So what happens if you remove this training sample and take a look at the response, the change in the model's reaction on this test sample? It's so hard to express in one sentence as well. And they, and then we are asking people, we also proposed like different options. Maybe in one case, you can also remove several samples in the training set and see what happens on this single test sample. In the other case, we also asked them whether they find it useful to remove multiple samples in the training set and looking at their impact on multiple test samples. So more many-to-many cases. In other case, we asked them whether they find it useful to not just look at removal of training samples, but actually addition of training samples. Yeah? If they add these samples, what kind of changes will they see? Can they kind of predict this result without having to retrain by themselves, right? And for the majority of cases, actually no one found the usual definition of training data attribution given by leave on out retraining useful. So 0 here means no one found this useful. Actually, what they find more useful is group influence attribution, for example, or kind of explaining multiple test points at the same time, so many-to-many kind of impact, or going beyond the removal and introducing addition kind of notion in training data attribution. So this is kind of giving a strong message that we should probably shift our focus to something more useful in practice. So with this motivation, let's take a look at group attribution. So instead of removing a single sample, let's say we try to remove multiple samples and try to see the impact of these. So we have, let's say, Z2, Z4, and Z7 removed together. And I'm going to say these are subset S. And I'm interested in the impact of loss at Z when you remove this subset S from the training set. Yeah, so the question is quite simple enough. And one methodology for one approximation to make this faster is called data models. So data models is, again, a linearization of the mapping from the training set through the parameter to the final loss value. You're linearizing this whole procedure. And the way you linearize this is by introducing a set of parameters. So you're introducing one coefficient per training sample. It's called beta j. So for example, now you can do approximation of the loss value for a particular test sample, given that you're actually not removing, but actually including S in this case. So let's say you're including S and removing whatever is not in S, okay? And then you're going to approximate this quantity by summing over all the beta values corresponding to the training samples in S. And then, yeah, you can introduce some kind of constant value here, beta note, to make this fit better to your data. The other way to write this down is g beta s, which is the approximated function here, which is the linear, basically the linear dot product between beta as a vector and the indicator function, which is giving you element-wise 1 or 0, depending on whether the index is in S or not. Yeah, so that's a linear function with binary inputs. So, and what you can do actually is to find values of beta. For computing the values of beta, what you have to do is you come with a few examples of S, yeah, and actually do retraining for these S, okay? So let's say your S looks like this, so you're only excluding this and this point, and then you have to do retraining in that case. And then you're gonna get, for example, 0.693 as the loss value for the test sample, okay? And you do that like 7 times here, and you're gonna get 7 rows in this table. It's very expensive, right? Because you have to train 7 times. But the point is that this is probably still better than having to train combinatorially many times according to the number of training samples you have, right? Because the number of subsets for a huge set is exponentially many, and you don't want to compute all these cases, so maybe you can subsample from this. And then the hope is that when you fit your betas for these finite number of cases or linearly many cases, then probably it generalizes well to the rest of the exponentially many cases. So that's the intuition here. And I was basically copying and pasting the same table structure from the Lime slide a few weeks ago, because the computation is exactly the same. In Lime, we also computed we estimated a linear function. We basically came up with coefficients for every feature in the given test data, and we approximated the final loss value in terms of the summation over all these coefficients, depending on which feature is present. The same is true here, right? We are approximating the final loss value depending on which training data is present. So conceptually, it's much simpler than influence function, because we don't have to kind of go through this complicated procedure of having to go from training data to parameters and then to final test behavior. but we are kind of approximating this full procedure with a sparse linear function. The reason why I call this sparse linear is because you also put this L1 regularization term, which is inducing sparsity in beta. Okay, so yeah, this is also called lasso regression. Yeah, if you have L2 loss for fidelity term, and if you have L1 regularization term, then this is called lasso. Yeah, so again, the caveat is that you need to come with some example subsets of the original training set, and then you need to have the ground truth loss value for each of these cases. These are given here. So these are the only computationally heavy part, and actually very computationally heavy part. Once you do that, then you can do this, right? I mean, computing betas based on these is relatively easy. It's just a simple application of lasso algorithm. You can do gradient descent, for example, here. Right. So I put data models and Lime apples to apples here. They look very similar, right? So you have this approximating function G beta here, and then you have the ground truth, which is given by this after retraining. And for Lime as well, you have the ground truth here and the approximation here. Maybe the only difference is that for Lime, you are using some kind of weighting scheme to make sure that the perturbed inputs should be local, right? So we are perturbing the inputs, but we put more weight on the samples that are closer to the original input. But for data models, we don't necessarily do that. I mean, the authors do not do it. I mean, maybe it makes sense in some cases to put this kind of weight, but yeah, I don't think it matters too much for data models. And then you have some sparsity term. You can use L node or L1 for doing this. Yeah. So let's do a bit of numbers to kind of see how heavily computationally heavy this is. So you have training subsets S1 up to Sn. And the kind of experiment that they did in this paper, data models predicting predictions from training data. They used CIFAR training set. And you know, CIFAR training set has 50,000 samples. And the size of subsets they used was alpha equals to 50%, so 25,000 samples for each subset. And they sampled actually 300,000 subsets like this. Okay, that's a huge number. That means they had to retrain the whole model 300,000 times. How much CO2 is that, right? Just to explain one model, right? I think it was a very small model actually. Right? And they were processing these training sessions at the rate of 40,000 models per day on 8 times 800 GPU machine. So it's not actually too bad, like compared to the number of models that they are training, but still, you need to have sufficient resources to do this kind of crazy experiment. But now with this 300,000 data points, they can fit this linear model. And they say it works well afterwards. Okay, so that's one example of how one could do data attribution, like group-wise attribution, yeah, to training data. Okay, so let me try to wrap up the training data attribution and explainability part. So now let's try to go beyond removal. Okay, the question is whether we can simulate adding data as well. Training data attribution based on leave on out or leave subset out, they're focused on removal, and the question is how efficiently we can simulate this, yeah, using influence function or track-in or data models, right? We can also try to simulate addition of training data. I believe this is actually possible, right? Based on the viewpoint of retrieval as well, right? So we can probably do some kind of embedding of the training samples to the embedding space. and the test samples to the embedding space. And then in the same embedding space, when we have a new set of new samples to include, we can also map them into the same space and measure the dot products, right, between these points and the test sample of interest. And then that's probably going to tell me how much increase or decrease in loss values for this test sample they will bring into the model, right? So maybe we can do some kind of extension of what's already done in training data attribution for the addition instead of removal. I see no problem in just doing that and checking out how well this is also approximating the addition of training data. And this is an open question. I haven't done it myself, nor did I see anyone doing that. So wrapping up the training data attribution, we looked into mostly on leave on out retraining. So we first have to compute the leave on out ground truth to at least to do some kind of evaluation. Yeah, and then we have different ways to approximate this using, for example, influence function or tracking or data models. We can also have a retrieval perspective on this and kind of bring in different techniques from retrieval literature for this problem. And then the question is why leave out, right? Why not add more data or do something else here? Okay, and now let's do a bit of conclusion for explainability in general. So the goal, again, is to make something complex to interpretable to humans. And goals are quite varied. So it's different from like accuracy evaluation, which is kind of easy. But here, people have different end goals like debugging or building trust. And there are always a three-level abstraction, real-world problem, well-defined task, and an approximation of this task. And evaluation is one, faithfulness of this approximation, and two, efficiency. And maybe there can be some end-to-end evaluations to make this more relevant in practice. We looked into feature attribution and training data attribution. So evaluation-wise, we usually care about counterfactual kind of simulations. What happens if you remove or add or modify training data, features, and so on, right? And the goal is to do this more faithfully and efficiently. In terms of methods, we usually rely on linearization of the counterfactuals. It can be around a single test point features, or it can be also around the training samples that contribute to the test point prediction. Gradients are usually used in this procedure, but gradients tend to be very, very local. It's only showing the approximation around the point of interest. And there are also other methods for kind of extending the scope of this linearization beyond just a single test point, test features, or a single set of training data, all the way up to different variations. Okay, so now future research topics in this domain. So training data attribution, I think there's a lot of promise in kind of extending this to many influences, simulating addition, baselines. We need more baselines from retrieval. Okay, and now this is a little bit more interesting, connection to other topics. So we can combine training data attribution with OD generalization, for example. So we can try to attribute the lack of generalization to certain out-of-distribution cases back to the training data. In this case, in particular, addition will make a lot of sense because the typical way to introduce enhanced generalizability to out-of-distribution is to exactly to include those out-of-distribution samples in the training and make them not out-of-distribution anymore. So that's one possible topic. In terms of fairness, people have been looking into this domain also quite a bit. So it's not like totally new area to explore, but yeah, there are some initial works here. attributing model disagreement to data points. So this is also something that we are also looking into. So models behave differently, and when we say models are different, what I mean in general is they react differently to certain data, right? Given some data. So for the majority of samples, actually, models are kind of rather doing similarly. You have like hundreds and thousands of models trained on ImageNet pre-training data, and they're more or less similar for the majority of samples. But there exist certain samples where they are behaving very differently. And I find it very interesting that models are still showing very diverse behaviors on a certain set of samples. So I'm interested in kind of looking into those subset of samples where models are actually different. Right, and thirdly, there's potential work in attributing probabilistic models to training samples. Yeah, so we're going to talk about probabilistic models after the Christmas break, and I haven't seen much work on kind of connecting Bayesian neural networks and probabilistic models and training data attribution. The question here is which kind of samples are contributing to some good calibration of the model, for example. So I think these kind of questions could be quite interesting. Finally, there are some ideas around combining feature attribution and training data attribution. So for example, you can attribute back to training data, but within the training data, there may be some features that are kind of contributing, or there may be some shared features across different training data. And if we can kind of attribute to a group of samples, but with shared features, maybe this could be also a useful signal for model debugging, for example. And this is also related to something called prototypes that people have been looking into. So with this, I think I'm done today.